Video, we're going to discuss the maximum sum subarray problem. So in this problem, you're given an array A of numbers. They can be positive, negative, integer, whatever. And your goal is to essentially sum them up to be as large as possible. So first let's look at the easy version, which is the subsequence version. So in this version, we're allowed to skip entries. So for example, we could pick 4, 6, 15, 16, and 3. And this is really easy because all you have to do is either you just pick all positive numbers. And that maximizes the sum. And in particular, if there's no positive numbers, well, that means you just pick the empty set, which has 0 sum. So you just skip all the negative numbers and it's super easy. Now, what we want to consider is the substring version. And essentially this means we can't skip middle items. So need to pick a subarray of the form AI through J. So this means you have to select them all continuously. You can't skip anything. So for example, this would be a continuous subarray. It goes from I to I plus 1. It doesn't skip anything. You could also do this. But you would not be able to skip 7 minus 7. Which we'd want to. Like, ideally, we don't take any of the negative numbers. But we have to include them all. So that's the goal of the problem. So we want to find the max overall I less than j, or less than or equal to j, of the sum from k equals I to j of a k. So that's just the sum of all the elements in A through J. So this is the same as the sum of A I through J. That's what we want. Now, how can we do this? Well, ideally we just pick everything positive and just try to find a big interval of positive things, say like this, lots of positive numbers. But the issue is if we use this type of greedy algorithm, we might skip other entries. So for example, maybe instead of 4, this could have been like 100. And then it would be worth taking the minus 7 because it's offset by how big the 100 is. So in general, we can't use a type of greedy strategy. We need to solve it some other way. Now we could solve it just directly by brute force. So the brute force algorithm just literally considers all pairs. I at most j, and just compare all their sums. And compare it to the best so far, to the 3 C's. So we're literally just checking all pairs, computing their sum, and picking the one that's best. So the issue with this approach is how many pairs are there like this? Well, there's O of n squared pairs. And for each pair, we're doing this sum operation right here. And really the sum is this sum, which you have to implement with like a for loop. And so we're really hitting O of n, we're doing O of n work per pair to compute the sum of everything between, in the worst case. So you could imagine the case when I and j, I is very small and j is very big, then you're going to hit almost everything in the array when you do this. So overall, you get T of n is O of n cubed. So not very good. We can do much better. So the first way we're going to try to do better is with divide and conquer. And the idea is pretty simple. If you have some array and you want to compute the max sum subarray, well, you can just split it in half and either the best array, the best subarray, is on the left side, the best subarray is on the right side, and we can compute both of these recursively. Or there's this third case, which is the best subarray. So let me just say these are best. The best subarray crosses the middle. So is in both sides. Okay. So for the left and the right, it's easy. We can just recurse. But how do we determine these crossing subarrays? And the idea is going to basically be similar to merge sort. So we recurse on the left, we recurse on the right, we compute the subarray that crosses the middle, and at the end, we're going to return the max of all three, because the best one has to be in one of these three cases. There's nowhere else it could be. That's the whole array. So then the entire algorithm is just return the max of left, right, and crossing. So let's focus on how to find these crossing subarrays. So the key property of a crossing subarray is it has to cross. So for simplicity, let's assume we have an even array, just for illustration. So we have an even size array, and there's two midpoints basically, which is m equals the floor of n over 2 and m plus 1, which is the same as the seal of n over 2. So the key thing about a crossing subarray is it has to include both m and m plus 1. So crossing must include m and n plus 1. Then the key question is, how do we extend this? We'll call it C. So how do you extend C to include more things? If we want to. So it might be optimal to just return C as is, but it might be helpful to extend C. So how can we extend C? So the idea here is, well, let's check the left side and the right side. And if it's worth including those elements, then we include them. So we're going to tentatively add it and see what happens, and if tentatively not add it and see what happens. So it's kind of like a DP thing. So we'll just focus on the left. So we're going to extend C to the left, or towards the left. And the idea here is we either include AI, or I technically if we're keeping track of the indices, or we don't. So leave C as is. Now, how do we know whether we should do this or not? Well, we're going to recursively figure out what it'll look like if we include AI, and if that's better, then we'll do that. So we do this part recursively. And then we compare both options. So that's the idea. Now the implementation is actually simpler. So in terms of the implementation, we really just need to keep track of the tentative best, and then we always assume we add things to it. So keep track of the tentative best sum, and we'll call that sum S, and the end of it. Though if our goal is just to compute the total sum and not the indices, we don't really need that. So we might also want the end, the left end. So we know the tentative best sum, and we're at AI. Well, the sum afterwards will be, so the tentative sum, which I'll call S prime, is going to be S plus AI. And so we're just going to keep looping through, and if S prime is better than S, then S becomes S prime. So we just keep track of the best so far. And then at the end, we're going to return it. So overall, what this would look like is we have some loop that starts at m minus 1 and goes down to 1. And it keeps track of the sum. So at the beginning, the sum is exactly am plus am plus 1. And then we try to extend it. So we have S prime is now S plus AI. If S prime is better than S, then we update it. And in total, that'll give us the best sum. That's the extension to the left side. Okay, so overall, what we're really doing is we're recursing and including AI if it improves our performance. Otherwise, we're not including it. And then we just take the max overall at the end. And then we do the same thing for the right. So overall, we've determined the total crossing sum. And so we can return the max of all three. So what's the runtime? Well, we get something like merge sort immediately because we have two recursive calls. Remember, we recurse on the left and the right, and then we do something in the middle. Well, in the middle, how much does the crossing procedure take? Well, if you just think about it in terms of the for loop, it's going to clearly hit each array element at most one time. And so it's going to be O of n total when you do this for both sides. And so we get O of n. So it's similar to the merge procedure, right? So the merge procedure for merge sort looks at each element at most once as well. So then because it's like merge sort, recurrence, we know it's O of n log n. Or you could look at the recursion tree, but it's exactly the same recursion tree. Okay, so what's the proof of correctness? Well, I kind of said it in words, and again, it directly follows from this property here. Either the best subarray is on the left, it's on the right, or it crosses. For the left and the right, we get these for free. We know these are correct by the induction hypothesis, i.e. the recursion fairy. And then the middle part we know is the optimal max crossing, because by definition, we keep extending items only if it improves our sum. So overall, we end up checking implicitly all possible subarrays, and we've just picked the best one by brute force. So overall, we get the correct crossing subarray, which to be formal, you could prove by induction, but it's kind of clear. And then because we take the max of all three, and the maximum has to be in one of those three cases, the whole thing's correct. So that's the correctness proof. Okay? So correctness, induction, and the property before. And this proof is very similar to like a dynamic programming proof, right? So we try it or we don't, and then we know it's optimal. So that's the recursive version, the divide and conquer version. Now there's also a very nice dynamic programming approach we can take. So let's look at a dynamic programming approach. So first we need to define some kind of subproblem that we want to solve. So remember, our goal is to compute sum ai through j. Now if we want to beat n log n, we need to have our subproblems have only one parameter. If our subproblem was of the form I comma j, then we'll definitely get O of n squared, because it's just how many subproblems there are. So we want to have some subproblem that depends only on one parameter. So for example, we could have our subproblem be defined on I, and the goal could be to find the best j. So that way we only need one parameter. So the idea here is we'll only keep track of I, and we recursively compute the best j. And if we do that, then we have all the lengths, and then we can return the max over all I of our subproblems. But this is the main idea. So now how are we going to actually implement this? Well, we're going to focus on lengths instead of literally computing j, but you can change and modify this algorithm to find j if you want. So what are we going to do? Well, let's define the max sum subarray of I to be the sum of the max sum subarray in ai through n that must include I. So the reason why we must include AI is because this symbolizes the idea that we fix an I, we're starting at I, and we're just slowly extending our array until we hit the optimal j. So we're fixing I. So pictorially, we'll be at some I, and we have some subarray. We want to extend it until we find best j. So it's kind of like the crossing thing a little bit. So that's what we want to solve. So how do we actually solve it? So let's recursively define this function. So this is going to be, what are the cases? Well, obviously we need to have an element for this to make sense. So if I is greater than n, the maximum subarray is nothing, because we can always take the empty set, and the empty subarray has sum 0, it has no elements. Otherwise, we can either extend our subarray or not extend it. So we want to take the max here, we do extend it, so we have AI plus the MSS of I plus 1. So we're going to take the max sum for the subproblem I plus 1, and then we have to add AI, so we're just going to add AI to it. So we can do that, or we can just take AI as is, not extend it. So again, it's similar to when we computed crossings, where we're tentatively deciding should we extend or not, versus in crossings where we decided should we include AI or not to do the extension. Okay? So that's the procedure. Now what's our return? Well, we need to try every possible I position. So we're going to return the max over all I from 1 to n of MSS of I. And that's our algorithm. So now let's do the DP steps, and then we'll talk about the correctness. So what's the first step? Now that we have our formulation, we need to identify the subproblems. So what are the subproblems? Well, we have a subproblem for each I, and I can be anything from 1 to n plus 1. So subproblem for each I from 1 to n plus 1. N plus 1 just because in the recursive case, we might have MSS of n, and then this will be an n plus 1 in that case. Okay? And I guess technically, we should also include 0 here for the empty set. So we have those subproblems. Now what's data structure we're going to use to store all the intermediate results or all the partial solutions? Well, the easiest thing would just be to use an array. So we'll have an array M that's indexed from 1 to n plus 1 so that it can store each subproblem effectively. Okay? The next part is dependencies. So if we look at the definition of the subproblem for I, it only depends on the subproblem for I plus 1. So if we draw out our data structure here, we have I from 1 to n plus 1. Then I only depends on I plus 1. So we just have this dependency arrow here. So what's our eval order? So to ensure that we've completed subproblem I plus 1 before problem I, we can just iterate up to 1 starting from n plus 1. So this is equivalent to having a for loop for I equals n down to 1. It's n instead of n plus 1 just because we're going to do our base case outside of the loop. Okay, now we have our runtime /analysis. So what's the runtime? Well, there's O of n subproblems, and in each subproblem we do a max and a sum, maybe an if statement, so that's just constant work per subproblem. So this is subproblems, work per subproblem, ignoring recursion. And so the total is O of n. Just to fill our array M with these entries. At the very end, we also have to do this final max, but this final max is just going to be an additional O of n because we check every entry of the array. Then additional O of n to take max over whole array. Okay? So we get O of n plus O of n, which is O of n. So it beats the O of n log n crossing algorithm. The space complexity, though, that's going to be O of n as well. Just because we have to remember, we keep track of n different things in our array M. Now this can be reduced, so you could maybe tweak it to only remember the I plus 1th entry and do some clever tricks to get it to O of 1, but we don't really care too much about space, so I'm just going to leave it as is. And then F, this is the full algorithm. So what's this going to look like? It's literally going to be you slap this recurrence into your for loop. So we're going to have M1 through n plus 1 initialized at all. We'll initialize this to be minus infinity, say. For our base case, we define mn plus 1 to be 0. Then we're going to have a for loop. And what happens inside the for loop is we'll just do the recurrence, but replace MSS with the M. So we're just going to take Mi is going to be the max of AI and AI plus Mi plus 1. And at the end, we're going to return the max over all I from 1 to n plus 1 of Mi. So here I included the n plus 1 there, just so we get that 0 built into the max, so we don't have to separately include a 0 like before. But this will be the full algorithm. And we can call this max sum subarray of A. So that's it. That's the entire algorithm and analysis. Now, we still have to consider the correctness. And again, for DP things, you don't have to be super formal, but you just want to give some argument. So what's the idea here? So either the max sum subarray is empty, or it has an element. The entire algorithm, at least the last step, which this is what I mean by the last step. So that last step is just saying, find the best first element, or find the subarray where we define the subarray based on an anchor point, which is the left point. So this is just a way to define a subarray. So if it has an element, there's a first element, we directly, by brute force, find the best first element, and then using the recursive function MSS of I, then guarantees for the best I, so let's say the best first element is I, MSS of I gives us the best endpoint j. And so the entire thing, AI through j, is going to be optimal. In particular, the reason MSS of I is correct is just because either it's just AI, I mean, that's a subarray that includes I, or it's something else, it's something longer. And that longer thing will be the optimal longer thing plus AI. So it's the optimal sum you can get from the rest of the array plus AI, or concatenated with AI. All right, so those are the options. If we include AI, then it has to either be just alone, a singleton, or it's including other things in AI plus 1. In particular, it would have to include AI plus 1. And so the recursion fairy is going to correctly generate the max sum you can get here, and obviously the max sum there plus AI gives you the max total sum that has to include AI. So that would be the proof.